Hello there. So I guess we're going to start again. This is our week of Greco-Roman mathematics. It's very, very, very much worth pointing out and important to keep in mind. We are jumping about 1,000 years from where we were last week. So don't make false comparisons. Don't think, hey, wow, the Greeks were doing all these amazing things while the Egyptians and Babylonians were just doing these other things. We are jumping 1,000 years in history. So it will feel different. It's still ancient. Without a doubt, we're looking at ancient mathematics, but it's that there's a lot of in-between years of progress going on here. I don't know how much I want to say anything about Thales, except for perhaps to pronounce the name Thales. It looks as if he may have proven some things, which is interesting. We don't have any records that go back that far, perhaps unsurprisingly. But everyone who came after him said that he had not only some observations, because his observations seem relatively unsurprising, but he may have had some proofs of them, and that's moderately interesting. I do want to say quite a bit about the Pythagoreans one way or another, and some things that you may have expected and some things that you see that Suzuki wants to talk about. And I like Jeff's focus here, so I'll probably tend to agree. There is one thing that the Pythagoreans were mentioned for that I think is worth pointing out, just because it's probably very different from the way you would think about it, and it's a nice other way to think about it. So regarding the Pythagoreans, and I am trying to give credit to the Pythagoreans in general because we tend not to know which of them did what. So there's not a lot of particular credit I can give to the Pythagoreans. But it does seem as if they knew that the sum of odd numbers gives a square number. It's worth pointing out the way they probably thought about this. They definitely did not do this using anything remotely related to something like induction. They probably did this by making little pictures like this. And then noticing that as you started with a square and then added some more odd numbers, you got a new square, and added some more odd numbers, you got a new square, and added some more numbers, you got a new square. That's probably what the Pythagoreans had in mind there. Okay, somehow, and this is going to be a little weird, but I think we'll make it do. I'm not sure how the volume setting will work, and suddenly that matters. I want to do some things about the Pythagoreans in music. So let's not show you very much, but I will come back and show you. Always doesn't work. That's nice. But in any case, show you our course content so that you can see where to find the things that I'm looking at. Let's make it bigger so that it's not crazy tiny. I don't know why the videos are suddenly embedded as videos. I'm not complaining, but it's a little strange. So there was Thales. We said some things about the Pythagoreans already. The Pythagoreans are largely responsible, intriguingly enough, for what amounts to the major scale upon which most Western music is built. That's a pretty big credit that might be neglected. They tended to use this instrument called the monochord, which is rather boring. It's just a string. That's the end of my story. It's just a string. So there's a monochord. I guess I could make that bigger, but you can make it bigger if you want. Here's a cute picture of Pythagoras standing in a monochord that will eventually load. There it is. All right, so there's a cute picture of Pythagoras standing in a monochord and a cute picture of Pythagoras playing some bells. It's worth pointing out that I'm not giving you any pictures of these people because of the fact that we have no idea what they look like. You'll see pictures that claim to be of these people, but they were made 1,000 years after these people were around. No one has any idea what any of these people look like. When we start having ideas what people look like, I promise you I will show you pictures of them. All right, we are going to play with music, and to do so, I'm going to use this piano. I don't know how much you need to see what I'm playing, but I also don't know how much I'm going to write either. So there it is. I'm going to use a piano because I know my way around a piano. Surely this is entirely anachronistic. There's important reasons why pianos can't exist given the tuning that the Pythagoreans were using. Okay, but here we go. Let's see how this works. I hope that's loud enough that you guys can hear it, but I think it probably is. We're hoping. If it isn't, this is going to be a disaster, and sorry. So, all right, I just turned it up a little bit louder even still. So what the Pythagoreans noticed, and I guess I'll put this down and just play some things. They noticed that notes that were twice the frequency or half the string length sounded very similar. That was the first thing they noticed. And we can do another example of that. Here's a note that's so that's doubling the frequency and then quadrupling the frequency, or halving the string length and then quartering the string length. So they noticed that multiplying the frequency by 2 gives things that sound similar, and so we will call these, we now call these octaves. It's a little strange to start with something that has the number 8 in it, because it has nothing to do with the number 8 yet in this story, but that's what we now call them, and we notice those things sound similar. The Pythagoreans also noticed, and this was convenient for them because it's worth pointing out the Pythagoreans were basically a cult worshipping, and now you have an ad for HBO Max. That's great for everyone, I'm sure. They had a cult. They were a cult worshipping small numbers. Anything that could be expressed in terms of small numbers was more valuable to them. And so having this nice 2-to-1 ratio, yeah, this is a good thing. They like small number ratios like that. They also noticed that the ratio 3-to-2 was appealing. This is what we now call a fifth. I don't know exactly why I'm writing this here because it's tiny on your screen if you can see it at all. But I am saying the things, and that's probably good. So a fifth is that interval. That sounds pretty nice. Here's another fifth. And those notes sound nice together. And the Pythagoreans noticed that, yeah, these notes sound nice together. Now, it is worth noting, I will turn the piano off. Maybe you seeing it is not so important in any case. It's worth noting that we have then a new interval that we make. We have an interval from the bottom of the octave to the top, from the bottom of the fifth to the top, but we can go from that fifth note to the top of the octave. It's worth noting 3-to-2 is the same as 3/2 to 1. So the interval between the top and the middle note is 2-to-3/2, which is the same as the ratio of 4-to-3. This is a fourth. And unsurprisingly, these notes should sound good together. Also, let me not show you, but yes, play for you. So these notes are like, here is a fourth. Those sound pretty good. Or maybe those two notes sound pretty good together. So again, we have small ratios that are sounded, and that seems appealing. We could also, now that we have the top and the bottom and this one middle note in the interval from the middle note, we could take this fourth from the same starting point. So we could start at a given note and do 3 different intervals all from the same note. We started with our octave, which was this. That's one interval. We said fifths are nice, so we'll do it the same starting note and go to the fifth. That's pretty good. And we could go from the same starting note to the fourth, and that's pretty good. And it seems that the Pythagoreans noticed that, hey, these ratios all seem to produce nice things. That's good. We have the same game we played before, where we found the octave and the fifth, and then we found the interval between those two notes. We could do that game with the fifth and the fourth and find the interval between those two notes. To do that, well, all right, the fourth is also 4/3 to 1. So then we could have the interval from 3/2 to 4/3. That's the same as the ratio 9 to 8, which is a pretty nice number. These are still rather small numbers. And that is the interval between a fourth and a fifth, which are these notes. And that's pretty appealing. And that seems to work out nicely. And now I think I am going to switch back to letting you see what's going on as I play these notes. So let me see if I can do that. Here we go. And this is probably not going to work because it never ever works. Thanks. All right. So there's another ad for HBO Max, everyone. They're getting royalties for this, I'm sure. And so here's our notes again. What we have now is this interval, which is called a whole tone. And that's pretty nice. And that gives us something. And then the Pythagoreans said, well, this seems useful. What if we tried to build up as much as we can using this interval? So we will start at our starting point and go up an interval of a whole tone and go up an interval of a whole tone. And then we're in this tight spot because we've already defined this note. This, by the way, was our fourth. That is our 4:3 ratio. So if this interval is our fourth, and we've said we want to go up from here by 9 to 8 and 9 to 8, then we need to bridge the gap. And the gap from the note we just played to the fourth is not a nice number anymore. This is where the awkward numbers like 256 over 243 show up. This is not something that would be worshipped by a cult of small numbers. That's not a small whole number ratio. This gives us something that is a half tone. And notice the interval. I don't know why I played the second notes twice. This interval is the same as that interval, but that's not the same as this interval. The interval is different. This is a half step, and that's the next note that was designed to be put in the scale. And then they follow whole step, not there. All right, so start down here, whole step, half step, and then work your way up to the octave with as many whole steps as you can. And then a half step at the end because you have to end at the octave. You don't have a choice there. So this scale is designed by requiring us to keep the fourth, to keep the fifth, to keep the octave, fill in as many whole tones as you can, and then fill in the little gaps the way you have to. The problem is that none of these ratios work out in a consistent way. This leads us to, and I think I will let you see the board more clearly. This leads us to the tuning problem. That if we tried doing these intervals backwards, they wouldn't turn out being the same. There's the numbers just don't work out nice, is the bottom line. We will see more about this as we go forward. We will come back to music in a few weeks, but it is worth noting a couple different things about this while we're still here. First of all, to the ancient Greeks, music was part of mathematics. You might wonder, why am I talking about music now? To the ancient Greeks, there was this whole thing called mathematics, and it was divided into what is called the quadrivium. There's mathematics of space and mathematics of number. Mathematics of both space and number are divided into applied and pure mathematics. The applied mathematics of space is called astronomy. The applied mathematics of the pure mathematics of space is called geometry. The applied mathematics of number, oh yeah, that's music, which was originally, or at least in the ancient Greeks, a branch of mathematics. And the applied mathematics, the pure mathematics of number is arithmetic. So, okay, that's interesting. It's also worth noting and interesting that this is ultimately the origin of the major scale upon which Western music is built. So this is not a small thing. And this is why we make music the way that we do. I'm not saying that all music in the world is this way, but unless you listen to weird stuff, this is what all music that you ever listen to is based on. I sometimes listen to weird stuff. Weird stuff is great, by the way. And there's lots of other cultures and different ways that music is made. But the music that is most predominant, the music that you're usually listening to, is definitely built around this major scale. All right. That's fine. Let me come back to some documents here. And we will tell the piano to go away. Once we get to the piano, there's the piano again. All right, go away. No more HBO Max, thanks. All right. So what we should look at next, I think you probably could reasonably claim the Pythagoreans are best known for the Pythagorean theorem. I like, by the way, that it's at least called the Pythagorean theorem and not Pythagoras's theorem, because we definitely don't know that he was personally responsible. As we've talked about before, and we'll talk about again, it's all over the world, so it's hardly fair to even give the Pythagoreans full credit. But in any case, this is Euclid's proof of the Pythagorean theorem. And I think I don't want to talk through it in great detail, but I do want to, oh, come on. You can't get any bigger than that. All right, sorry about that being loud for you. Might as well turn that volume way down because we don't need volume anymore. All right, I want you to focus on this picture. First of all, and I don't think I'm going to talk through most of the text. You can read the text. The text is very readable. For those of you in geometry class, I imagine that Melissa is making you do stuff like this. For those of you not in geometry class, you could read this text and it will feel very much like high school geometry with a little more pedanticness to it than you're used to. But okay. It is worth noticing what the Pythagorean theorem says because many people have trouble with that. It says, if you have a right angled triangle, the square on one side plus the square on the other side is equal to the squares on the side containing the right angle. You would now call that the hypotenuse. So you would say the square on one leg plus the square on the other leg equals the square on the hypotenuse. Okay. But they are physically about actual squares. That is important and sadly, strangely neglected. I don't really know how people manage to do that, but the Pythagorean theorem is about areas. It's about areas of this square plus this square equals this bigger square. Okay. I'm not going to read through the text to pull out exactly the steps along the way. In particular, Euclid, this is Euclid's argument of the Pythagorean theorem. It's worth mentioning, I think Jeff mentions this also. Most of what is in Euclid's Elements is gathering of other people's works. So it is very reasonable to presume that Euclid's proof of the Pythagorean theorem is pretty close to the Pythagorean's proof of the Pythagorean theorem. It's not going to be drastically different. Let's look at some details here. There's some strange arguments that this line is actually straight, BAH, that this line is actually straight. Those are not terribly interesting. They're true, but they're not terribly interesting. All right. Then there's an interesting consideration made. These points are connected FC, and you see all these diagonal lines that are drawn in. Those are just connecting different corners of the triangle to different corners of squares. You can see that much. There's also this line AL that is going to be really important, that is drawn in so that it goes from the right angle either parallel to a side of the square, which I think the way Euclid says it. Yep, let AL be drawn parallel to BD or CE. Or if you prefer, it's perpendicular to the opposite side of the triangle because of the right angles in the square. All right, that's fine. What that line does is divides the big square into two rectangles. And these two rectangles are really important because what Euclid's about to show us is that this square has the same area as that rectangle. And this square has the same area as that rectangle. So yeah, the sum of the areas of these two squares is the area of the whole square. That's going to be nice. And the way that he gets us there, I actually didn't start timing. That's embarrassing. I tried so hard. All right, the way that he gets us there is by looking at this triangle ABD and this triangle FBC. Notice in particular, they both have side lengths from this small square. Okay, good, so those sides are the same. They both have side lengths from the very large square. All right, so those sides are the same. And this angle is the same as that angle because they both have a right angle and then this angle ABC. So this triangle FBC is congruent to triangle ABD by side angle side. They have one side, an angle, and another side. Okay, great. So these two triangles are congruent. And now here's the key step. Notice the area of this triangle, because here's its base and here's its height, is half of this square. The area of this triangle, because here's its base and here's its height, is half of this rectangle. So if the triangles which are the same are the half of the square and the rectangle, then the square and the rectangle better be the same. That's the point and the main idea here in Euclid's proof of the Pythagorean theorem. There's, if you read the text, it says, goes through the steps to get you there. We're halfway done. We just need to do the other half, and it's exactly the same. It's exactly the same. It uses this big triangle BKC and this triangle EAC. They're congruent for basically the same reasons. They both have a side of this square. They both have a side of this square. This angle ACE is the same as this angle BCK because they both contain ACB and right angles. So the triangles are congruent. This triangle is half the area of this square. This triangle is half the area of this rectangle, this side of the rectangle, for exactly the same reason. So this square is of the same area as this rectangle. And we're in a good place. So the sum of the areas of the squares is equal to the area of the bigger square, which is what we wanted to show. So that's Euclid's proof of the Pythagorean theorem. It's fine as far as things go. I'll say a little bit more about Euclid in a minute, because I'm really talking about the Pythagoreans now and not up to the time of Euclid yet. The other thing the Pythagoreans did, which is related to that, so now I will turn this back off, is working with Pythagorean triples, which obviously are related to the Pythagorean theorem. By the way, you should remember we talked about the Pythagorean triples in, it's nice erasing today, I don't know why, but I'm not complaining. We talked about the Pythagorean triples in Plimpton 322 with ancient Babylonians. Once again, about 1,000 years before this, they had lists of Pythagorean triples there. It's mentioned in the text and worth pointing out, the Pythagoreans had ways of producing Pythagorean triples, starting with an odd number. I will write my odd numbers like that. Then taking that odd number, squaring it, subtracting 1 and dividing by 2. If you do some simplification here, make a difference of squares, you get 2n plus 1 times 2, or 2n plus 2 times 2n all over 2. And lots of 2's could cancel there. This gives us 2n times n plus 1. Okay. And then if you let c equal 1 more than that, then you get 3 numbers that do satisfy the Pythagorean relation. A squared plus b squared does equal c squared there. You could do those computations. The algebra is not hard. This is basic algebra, and I'm sure you can handle it. And this is the kind of thing that was in that Plimpton 322 tablet in ancient Babylon that we talked about last time. All right, let's now go back to our course materials. Which never works, and we accept that. All right, there's that. It's worth, I'm not sure I'm going to write anything. In fact, I'm sure I'm not. But one of the Pythagoreans was someone named Hippasus, who is credited for being the first person to find an irrational number. That is a number that cannot be expressed as a ratio of whole numbers. You should think about the context here. I had mentioned that the Pythagoreans were a cult worshiping small number ratios. If someone comes along and says this number can't be expressed as any number ratios, he's going to not be very popular. Different levels of what happened to him are told in different stories. Some include him being drowned before telling them this. All right. The number he found, by the way, was probably the golden ratio. The ratio between a side of a regular pentagon and a diagonal of a regular pentagon, which is the golden ratio. All right, let's talk about Hippocrates. This is not the medical Hippocrates, so don't get confused. But Hippocrates was responsible for the first derivation of an area of, wow, that's really slow. The first derivation of an area that was not a polygonal area, a curved region area. In fact, the curved region is this segment, this piece here, the darkest shaded region, maybe AECF. That is called a lune. It's made, I hope you can see from the picture, by taking a circle or a semicircle if you wish, and then drawing in, me pointing at the screen doesn't help you at all, drawing in this diagonal and then making another semicircle on that diagonal, cutting the original circle out and seeing what you have left. All right. At this time, this is proved by Hippocrates. Hippocrates is going to use some different pieces to do this. I guess going back to the picture is probably the best place for you. He's going to use the fact that the ratio of the side length, or the diameter of a circle squared, is proportional to the area of a circle. Notice this is not the area formula for a circle. Hippocrates probably didn't know a proof for this fact, but it did seem reasonable. It looks as if circles are similar, and the larger the circle you get, it should be proportional, and area is proportional to a square. So it does seem reasonable. It is unlikely that Hippocrates had a proof of this. We will talk soon about who did have a proof of this, but probably not Hippocrates. All right, so moving right along. So I claim that Hippocrates has an area formula for that dark shaded region. And what he's going to show actually is that it's exactly the same area as the lightly shaded triangle. And obviously he and anyone else who ever wanted to could find the area of that triangle. So that's the goal. Let's see how he manages to do this. He does know the Pythagorean theorem. That's around at this time because we just talked about it, and that was before Hippocrates. And he will definitely use that here, in particular for this triangle. He also knows, by the way, it's worth pointing out, he knows, and I think it was proven at this time, in fact, probably before, I think this is one of Thales' results, that if you put a triangle inside of a semicircle, then this angle is a right angle. So he does know that. And in particular, if you make it at the midpoint down here, then you have an isosceles right triangle, and this is also an isosceles right triangle. Fine. Given all of that, we know from the Pythagorean theorem that 2 times this side equals this side, or 2 times this side squared equals this side squared plus this side squared. That's printed in this if you're looking at the whole document. That's down here on the bottom. Yeah, there it is. So there's the Pythagorean theorem. That's great. And from that, well, we also know that the ratio of this semicircle to its diameter squared is equal to the ratio of this semicircle to its diameter squared. And so the area of this semicircle is proportional to the diameter squared, and this one's proportional to the diameter squared. But remember, this here, AC, when squared, is twice of AO when squared. This particular work down here refers to AB. We could think about that also. That's good to know. So also, AO is half of AB. So AB when squared is twice AC when squared. So we find that this whole semicircle has twice the area of this semicircle. So half of this semicircle has the same area as that semicircle. That's good news. And now we're ready to do something. So that says this whole area AOC and then around this arc F is equal to this area ADC and around this arc E. We see they both have this white part in common. If we take that out from both of them, we're done. We're left with the dark shaded region on one hand and the light shaded region on the other hand. So they have to be the same. And that's what Hippocrates did. And that's pretty neat. The reason that's pretty neat is, I say again, this is the first known example of someone computing the area of a region that was not polygonal. And we were careful that you might say, but you use the area of a circle to do that, and it's not polygonal. And I say, no, we didn't use the area of the circle. We used that the circle was proportional to the diameter squared, but the proportionality constant was unknown. And that's true. It was definitely unknown in Hippocrates' time. It's also somewhat true that a proof that it's proportional to the diameter squared was not known in Hippocrates' time. We'll come back and get that very soon, promise. All right, so that's Hippocrates finding the area of an interesting shape. I probably did not want to do that. I probably did want to just go back to, yes, that never works. Go back to our course materials, great. Let's talk a little bit about Hippias and the quadratrix. So there are these three classical construction problems. The classical construction problems are indicated right here. Oh, that's very nice. Doubling the cube, trisecting the angle, and squaring the circle. That is making a square of the same area as a circle. These problems are hard. That's an understatement. Many, like a couple thousand years later in history, we will get to a justification for why they actually can't be done with compass and straight edge. But for our purposes, what's noteworthy right now is not that they couldn't be done at all, but they could only be done using something other than compass and straight edge. And that's why I want to talk a little bit about Hippias, because Hippias had this curve called the quadratrix of Hippias, as it says right here. And this allows us to solve some of these problems. In fact, all of these problems. I'm going to just talk about trisecting the angle because it's the easiest one to see. The quadratrix curve is an interesting curve. It's made not using compass and straight edge, which is why you can't use compass and straight edge to trisect the angle using this technique. But it is made by the following pattern. You start with this line segment CD at the top of a square, and you let it fall down at the same constant rate that line segment AC prime rotates going from AC over to AB. This animation here shows you exactly what I'm talking about, which is very nice animation. So look at this animation. You see that, yes, the horizontal line comes down and ends at the bottom at exactly the same time that the radial line ends at the bottom. And where those two intersect, that gives us the points on the quadratrix. It's a very interesting way to make a curve, but it's a curve nonetheless. And we can use it to do things like trisect the angle, because we can find trisections of lengths rather easily. And so if I trisect the length, then the lengths correspond to angles on this quadratrix because the angle lengths are matching up at each time as we move down. And there's more information here if you would like to see how this is used for the other problems. So those are some good things. Eudoxus, I mentioned I would talk more about circles. I will do that now. And actually now I will turn this off and talk a little bit about Eudoxus and circles. So Eudoxus is generally the one credited for proving that the area of a circle is proportional to its diameter squared. I again want to emphasize that the proportionality constant is not known. We will see next time. Archimedes will prove that the area is equal to the circumference times the radius. And that tells us an area formula. This is not quite an area formula. This is a proportionality. But it's a big step forward. It's a sufficient step for the kind of work we just saw with Hippocrates in the loom. Okay, so how does Eudoxus do this? Starts with a circle. And circles are mysterious because they are not polygons. So he says, well, it'd be nice if we could just use polygons instead. And pretty much that's what he does. He says that he knows with polygons, where he has area formulas for them, that the area of a polygon is proportional to its diameter. So what he does is takes his circle and puts a square inside and a square outside. And he says this square is proportional to its diameter, and this square is proportional to its diameter. So that's pretty good. And then what he does next is says, so it looks like it's between those two, but that's not good enough because there's lots of room between those two. So what he does next then is bisects each of these angles and makes an octagon and says it's still true that the area of an octagon is proportional to the square of its diameter. And that's one inside. And then he also makes one outside. That's not very accurate. I can draw a little better than that. Not much, but I can draw a little bit of that. That's it. So now he has an octagon outside. If you want, I can erase these and you will see the octagon more clearly. And he says, okay, so now this octagon is proportional to the square of its diameter, and the inner octagon is proportional to the square of the diameter, and the circle is stuck in between. Okay, but the key step here is he says we can keep doing this, and we can make the difference between them even smaller. We can have a shape with 16 sides, what I would call a 16gon, even if there's a more technical name for it. We can do that on the outside, we can do that on the inside, and we can make that. And the point here that Eudoxus makes is each time we're doing this, we're getting closer and closer to the circle. By the way, closer and closer, that should remind you, all of you, of calculus. So what Eudoxus is doing is something very, very related to limits here. And what he's actually doing is saying, no matter, and this should remind those of you who have taken your analysis course, no matter how small someone claims the error is between the polygon and the circle, we can get smaller than that by further subdividing. And Eudoxus actually wrote his argument that way. He said that any objection you have can be made, we can make it smaller than your objection. And so in the end, there is no objection to be had. This is Eudoxus's method of exhaustion. And this is his way of proving that the area of a circle is proportional to the diameter squared. It's a nice argument. It's an interesting way to do things. We will see some similar things when we look at Archimedes and getting us an actual formula for that. All right, let's see. I didn't start timer, so I'm not quite sure how timing is going, but I'm usually doing a decent job on that. We, I think, only have a little bit left, so that's fine. Let's come back, and yes, that doesn't work. All right. Euclid. So Euclid is shortly after Eudoxus. Euclid is interesting, of course. He's interesting in particular because he is the most successful textbook author of all time. That's probably what he deserves a lot of credit for. He gathered geometry and put it together in a way that was nicely organized. I don't think, and no one, well, experts don't think that he created much of that geometry. He gathered most of it. But he did, we do believe, create some things. The things that Euclid is most credited for creating is an algorithm for finding greatest common divisor by taking two numbers, dividing them, finding their remainder, and repeating that process until you get 0. That's the Euclidean algorithm for greatest common divisor, and we do believe Euclid devised that. He is also responsible for proving that there are infinitely many prime numbers. It's interesting because people think about geometry almost exclusively when they think of Euclid, whereas his original work was probably not mostly in geometry. A couple more people as we wrap up our Greek mathematics today. Oh, I meant to say this. So this is our Greco-Roman work. I think your silly code for today is wrestling. We are talking about Greco-Roman mathematics, not Greco-Roman wrestling, which is something else entirely that you could see in the Olympics. So there, your silly code for today is wrestling. All right, and so that's some things about Euclid. We also saw his proof of the Pythagorean theorem, so we've seen a little bit of his geometry work. Eratosthenes is an ancient Greek who computed a pretty good approximation to the circumference of the Earth. It's a fun thing. It's discussed in your text. There's a fun little video here of Carl Sagan talking about him if you want to watch that. If you only have like 2 minutes, you could start at 3:53 and he will tell you the story. And it's exactly the same as the story that Suzuki told him. I want to say a little bit more about one thing more, namely Apollonius. Apollonius wrote lots about conic sections. How much lots? Here's some work of his, but I don't know how much we're going to look at this. But it is worth saying, how much lots did he write? There were, I think, according to the estimates I found, 387 propositions about conic sections. That's a lot. Now, it is worth pointing out that both Euclid and Apollonius and others in ancient Greece tended to break things up into really tiny little pieces. And so each proposition was only a little tiny thing. It also is worth pointing out, as long as we're in the neighborhood of talking about Euclid and so forth things, I think I do want to make this point because I do think it's important. this whole structure of Greek mathematics and relying on proof largely was reflecting on Greek culture, relying on rules, which were largely designed to separate the people who were lucky enough to be free from the people who were their slaves. So I am very hesitant to glorify Greek mathematical proof, which was built on the backs of these slaves who were not so lucky to be able to spend their time doing such things, for what it's worth. All right. Conics. I want to say a little bit about conic sections, just so that you know why they're called conic sections. If you have been in the Math Learning Center, you might have seen this thing. It is a prop in the Math Learning Center. It is unsurprisingly a cone. That I think you believe. And as I mentioned, Apollonius proved lots of things, nearly 400 things about conic sections. I want you to at least see that conic sections are, well, conic sections, that is sections of a cone. Conic sections are things, wow, that's dramatic, like a circle. So that's a section of a cone, just if you took the cone and, yeah, you can't see this, but you don't need the board anymore today, and slice that off. All right, good. They are things like an ellipse, which is if you took the cone and sliced it at an angle. They are things like a parabola, which is what you get if you take the cone and you slice it down the side parallel to the main axis. So we're coming along parallel to this axis, which goes down the middle. You could also get silly things like two intersecting lines, which I guess is fine. But here's a parabola. You can also get a hyperbola, which is what you get when you slice a cone at an angle that is not just cutting off an ellipse, but which is going all the way. The cone, by the way, is viewed to go off to infinity. Now you can't see the bottom of the cone. This goes off to infinity. And these are the conic sections: the circle, the ellipse, the parabola, and the hyperbola. They are important curves. They are all, it turns out, although surely the Apollonius didn't write them as equations, but they are the quadratic equations that appear. They are the next most important curves after straight lines and circles. And as evidence that they are the most important curves after straight lines and circles, which surely the ancient Greeks didn't know, but just for your context, the conic sections are the shapes of orbits. So if something is traveling through the solar system, it either travels in a circle, almost never, or it travels in an ellipse like the Earth does and like all the planets do, or it travels in a parabola, which comets do close to, or it travels in a hyperbola, which is the path of some object that enters the solar system that's not staying in the solar system. So if something comes from outside the solar system and happens to get pulled close to the sun, then it will pass through the solar system on a hyperbola and then exit the other side. So that gives you some indication that these conic section things are important. Apollonius proved 387 things about these conic sections. Lots. An amazing amount of stuff that Apollonius proved about conic sections. Things like areas, things like how different pieces of it were related, things like tangents to them, things like segments perpendicular to them that are called normals, all kinds of things about conic sections. And that's where we leave our Greek mathematics. We will come back on Thursday and talk about Roman mathematics, thus completing our time of Greco-Roman mathematics before we leave that and go to other, perhaps more interesting cultures. Thanks. Bye. Bye, I said.